Hello students, welcome back. So we were in the discussion of a very important chapter, that is electrochemistry. I hope you have gone through all the lectures till now and you have covered the galvanic cell and you have solved a lot many problems. Okay, so we are going to take the discussion of the daily practice problem sheet that has been given to you. So that will be done only when the chapter is over. Okay, so I hope you are going through the lectures and you are supplementing it with some reading of NCERT. Okay, so today we are going to start the second portion of this chapter, that is electrolysis. Okay, so if you look at the word electrolysis, okay, so this word electrolysis is derived from two words, electro and lysis. Okay, now we have already done in organic chemistry, lysis means breaking, electro means it is a electrical current or a electrical energy. So through electrolysis what we do is we break a compound using the electrical current or electrical energy. Okay, so if we look at the definition, so we'll say that it is the chemical decomposition produced by passing an electric current through a liquid or a solution containing the ions. Okay, so if you are breaking any compound in aqueous solution by passing an electric current through it, then the process is called as electrolysis. Okay, so this is a very basic definition of electrolysis. Now we have already studied about Daniell cell. Okay, so what was Daniell cell? It was basically a zinc dipped in a zinc sulfate solution which is acting as a anode, whereas copper dipped in a copper sulfate solution which is acting as a cathode. They were joined through a conducting wire and a salt bridge was introduced. Now we have already done a lot of problem solving on that. We knew that it produced a EMF of standard EMF of 1.1 volt. Okay, so if we just attached external battery to a galvanic cell or the Daniell cell to be specific. Okay, so what will happen, because this cell is producing a EMF of 1.1 volt, if you connect a external battery whose EMF is less than 1.1 volt, okay, so the current would keep on flowing in the way it was flowing initially, that is electron was flowing from anode to cathode and the direction of current would be opposite to the direction of flow of current. Now when you increase the external potential, suppose it reached to a value of 1.1. So we will say that the cell was producing a EMF of 1.1 volt and externally we have also attached a opposing potential of 1.1 volt. So in that case what would happen? The flow of electron would stop and this cell would result in no production of electric current. Okay. Now when you are applying a potential that is greater than 1.1, okay, so the battery was producing a volt of EMF of 1.1 volt. Now you have attached external potential whose EMF, whose potential is greater than 1.1 volt. So what would happen in this case? The flow of the current would become opposite. Okay, now the electron would go inside the anode, okay, and it would cause the reduction of species in the solution, and at the cathode oxidation takes place. So we say that when we are applying a EMF or a potential difference greater than the EMF produced by the cell, then the cell will behave in the opposite manner. Okay, so it will convert into a electrolytic cell. Okay, so if you look at the basic setting of an electrolytic cell, so this is how you carry out electrolysis. We are having a solution in which there is a cation as well as a anion. Okay, now we have dipped electrode. Now this electrode can be inert electrode which do not participate in the chemical reaction, or it can be an interfering electrode that can interfere in the reaction. So we have taken a electrolytic solution and we have dipped electrode in it, and through external battery we are passing current into it. Okay, so when the current goes into the electrolytic solution, so the solution, the component of the solution would break into cation and anion. The cation we know will undergo reduction, okay, and the cation will migrate towards cathode, whereas anion would undergo oxidation and it would migrate towards, okay, anion would undergo oxidation and it would migrate towards cathode. Okay, so just let me make you understand this through an example. Okay, so we were saying that suppose we are taking any electrolyte, say AB, okay, so we are passing current through it, so AB electrolyte would break into A plus and B negative. Now this A plus would go at, because A plus is a cation, so cation generally migrates toward cathode. Okay, so cathode here would be negatively charged. Okay, so this terminal is your cathode. Okay, and this terminal is your anode. Okay, now if you just compare it with a galvanic cell, Okay, so in galvanic cell we were saying that oxidation occurs at anode. So you have to basically understand that the signs on the electrode is not uniform. It keeps on changing if it is an electrochemical cell or a galvanic or a electrolytic cell. Okay, but the basic function of the electrode remains same. At anode oxidation would take place and at cathode reduction would take place. Okay, now in a galvanic cell, when oxidation was taking place at anode, okay, so we are saying that it was having a negative charge, the rod was having the negative charge. Okay, so that was the negative terminal and it was anode over there. Okay, whereas in the cathode, if we are talking about galvanic cell, the reduction was taking place, okay, due to which there was a positive charge on the terminal, so that was your cathode. But if you look in a if you look in a electrolytic cell, okay, the cathode is having a negative charge and anode is having a positive charge. Okay, so this is the major difference between a galvanic cell, okay, and a electrolytic cell. Through galvanic cell we produce current, okay, whereas in a electrolytic cell, through those current or the chemical energy, we use it to break any particular compound. Okay, so in a galvanic cell energy is produced, whereas in a electrolytic cell electrical energy is consumed. Okay, so the electrolyte which is breaking in the solution, okay, as cation and anion, the anion would migrate towards anode and it would result in the oxidation of the anion, and the cation would migrate towards the cathode and it would have a negative charge and this would undergo a reduction and would get deposited at the respective rods. Okay, so this is the basic diagram of a electrolytic cell. Okay, hope this is clear to you. So during the electrolysis, the ions of the electrolyte move towards the oppositively charged electrodes. Okay, so this is the point which I am talking about. An electrolyte in electrolytic cell can be in a molten or a aqueous state. Okay, so this solution which we are talking about, it can either be a aqueous solution or it can be a, okay, it can be in the molten state. So when you pass current through that, so basically the electrolyte would dissociate into cation and anion. The cation, that is a positively charged particle, it would migrate to the negative electrode, okay, because opposite attracts. Okay, so the cation would migrate towards the cathode. Cathode is the negative terminal over here, and the anion which is having a negative charge would migrate towards anode which is having a positive charge. So you can see that the sign convention of the electrode has changed in a electrolytic cell. In a galvanic cell it was opposite. Okay. So if we talk about some more basic points, so we say that electrolysis is a technique that uses a direct current to drive an otherwise non-spontaneous chemical reaction. Okay, now this is also very logic. Okay, we can say this through our logic, because during a galvanic cell we were carrying out a particular reaction and that reaction has delta G negative, so that was a spontaneous reaction. Now what we are doing, we are increasing the external potential, okay, and we are trying to go to the backward direction. The backward reaction was non-spontaneous, so through the help of the external current we are trying to carry out a non-spontaneous chemical reaction. So we will say that electrolysis is a technique that uses a direct electric current to drive an otherwise non-spontaneous reaction. Okay. The voltage that is needed to carry out this electrolysis to occur is called as the decomposition potential. Okay. So let me take an example so that you are able to understand this. So let me just draw a electrolytic cell again. Okay. So I have already told you, in an electrolytic cell there would be a aqueous solution, okay, or a molten solution. Okay, suppose this is a molten solution. Okay, so this basically contains a electrolyte AB. Okay, so we dip two electrodes in it, through which we will pass the electric current. Okay, so we are joining it with a battery. Okay, so we are joining it with a battery. So we are sending electric current through this battery into the solution. So we know that this AB would initially dissociate into a cation and an anion. Okay, so we'll keep on increasing the potential. We will keep on increasing the potential of the battery, so that a potential is realized when this electrolyte AB will break into a cation and an anion. Now this cation, we know that it would migrate towards cathode. Okay, so this cation would migrate towards cathode and it would undergo a reduction and it will change into a species something like A. Okay, if it is a say H plus, so it will take up electron, change into a hydrogen atom, the two hydrogen atom will combine and hydrogen gas would be released. Okay, if it is a pure metal, say something like silver, so silver ion would take up the electron and convert into a silver. Okay, so this, suppose this is a metal, so this metal formed would start depositing at the cathodic electrode. Okay, if suppose this is the cathode, so we'll say that the A will start depositing at the electrode. Okay, at the cathodic electrode. Now if we talk about anode, so suppose we are having B negative in the solution. Okay, now this B negative would undergo oxidation because at anode oxidation takes place, so we'll get a gas B2 and 2 electron. Okay, suppose B negative is forming a gas B2. So suppose if this was your cathode and suppose this was your anode. In general what we say, okay, left hand side is always your anode and right hand side is your cathode. So this is just a general example. Okay, so where I have taken the left hand side as cathode, but in general the left hand side is always an anode. Okay, so we know that B2 gas would be evolved at anode. So at this terminal, which is the anodic terminal, we know that there would be evolution of a B2 gas. Okay, so this is the primarily working of a electrolytic cell. So through electrolytic cell we are carrying a non-spontaneous reaction. Okay, because if you take an example of Daniel cell again, okay, so we know that Daniel cell produces a standard EMF of 1.1 volt. Okay, the reaction is spontaneous, zinc 2 plus is reacting with copper and changing into zinc. Okay, sorry, zinc is reacting with copper 2 plus and changing into zinc 2 plus and copper. So this is a spontaneous reaction, E naught is positive, so delta G would be negative. Okay, so E naught of this was 1.1 volt. Now when we connected this entire galvanic cell system to an external battery whose potential was greater than 1.1 volt. So what would happen? The flow of current would become opposite. Now the electron would go inside the anode and it would cause the reduction of zinc. Okay, and it would cause the oxidation of copper. So in that case the reaction would become zinc 2 plus plus copper changing into zinc plus copper 2 plus. So this is a non-spontaneous reaction because we know that its delta G would be positive because the reverse reaction has a negative, gives free energy. Okay, so that is a non-spontaneous reaction, but it is made spontaneous by passing a electric current. Okay, so we have passing a direct electric current, DC current, to drive an otherwise non-spontaneous reaction. Okay, I hope this is clear to you. So now let us understand how we are going to predict the product of electrolysis. Okay, suppose in a container we had say aqueous solution we were taking. Okay, so we know that when we are passing current through the aqueous solution containing an electrolyte, so the electrolyte would dissociate into a cation and anion. Similarly, the water which was present in it would also dissociate into H plus and OH negative. So now there are two cations, A plus and H plus, that can go to the cathode and undergo reduction. Similarly, there are two anions in the solution. Okay, one is OH negative and the other is B negative. So that can go to the anode and allow the oxidation to happen. Now there are two interfering ions present at each electrode. So which one will get deposited or which one will evolve the gas has to be determined through certain rules. Okay, so one key point that you should remember is a substance which is having more reduction potential. Okay, now suppose there were two cations in aqueous solution, say one was having A plus and other cation say X plus. Okay, so both can undergo reduction when we are passing electric current through it and they can get deposited at cathode. Okay, now out of those two, one will be preferentially discharged at the cathode. Now it depends upon their, yes, you can guess it right, it depends upon the reduction potential, standard reduction potential. The cation that is having more positive reduction potential or less negative reduction potential has more tendency to get reduced. So that ion would be reduced first. Okay. Similarly, at the anode half or the anodic electrode, there are two anions that are interfering to get oxidized. Out of these two, only one will be oxidized. The anion which is having more positive oxidation state has the more tendency to get oxidized, or less negative oxidation potential has more tendency to get oxidized, and they will preferentially get oxidized as compared to the other. So we need to know the basic electrochemical series, okay, so that we can understand which cation or which anion has to be oxidized. So there are certain set of rules that has been given to us, okay. So the product of the electrolysis may mainly depend on the following factors. The first one is electrode potential of various reactions, okay, deposition or liberation at cathode and anode. So this is the point. If there are two cations that are competing, okay, to get deposited at the cathode, then that cation would deposit first, which has more positive reduction potential, okay, out of the two, or less negative reduction potential out of the two. Similarly, at the anode, that anion would be oxidized first, which is having more positive oxidation potential or less negative oxidation potential, okay. So that's how we'll predict which substance is going to get, which species or which ion is going to get reduced or oxidized at various electrodes, okay. The second point is over potential of gases with respect to the electrode at which they are liberating. So we'll talk about the over potential in a certain time, don't worry about that, we'll discuss in detail what is over potential. So there is a concept of over potential also that I am going to discuss when we are doing the electrolysis of NaCl. Similarly is the concentration of ions, okay. If the concentration of ion is more, so there is a more probability of that ion getting reduced because the number of ions has increased drastically, okay. So it depends upon the concentration of ion as well. And the fourth is type of the electrodes. If you are taking an inert electrode or a reactive electrode, because if a reactive electrode is taken, so that reactive electrode can also undergo oxidation or reduction. So again we have to check their reduction or oxidation potential to analyze what substance would be deposited at cathode or liberated at cathode or anode, okay. So these are the basic 4 points that we have to keep in our mind. The first is their reduction potential, basically their standard electrode potential, okay, their reduction potential we need to understand. The second is a concept of over potential. Third is the concentration. If concentration of any species is high, so we know that the probability of getting reduced becomes more because the number of ions in the solution has increased. And the last point is the type of electrode which we are using during the electrolysis of a particular electrolyte, okay. So these are the 4 points that you should keep in your mind. Now there are shortcuts also. So we are going to discuss all the different type of electrolytes and we are going to analyze which substance will get reduced and which will get oxidized. Because if you are clear with this concept, then problem solving in this chapter is very easy, okay. Just like the portion that we had just finished off, which is galvanic cell. So if you look at the theory of galvanic cell, if you understand all the different types of half cells or the electrodes, then the solving of question becomes very easy. So this is typically, okay, based on the basic theoretical knowledge of electrode potential, okay. So stick to the concept, keep reading, okay, keep doing the solving so that things become very easy to you, okay. Chemistry is not always logical. We also know that there are some parameters that has to be memorized, there are some parameters that has to be understood. That's why chemistry is one of the most intriguing, or like you can say that it is one of the difficult portion for JEE because it requires both conceptual as well as memory based approach, okay. So to master it, just stick to whatever I am saying, just follow a particular pedagogy and definitely you will sail through this journey, okay. So that is how the toppers are created, that is how results are produced. So you have to keep on understanding the concept and keep on solving problems on it so that those concepts are also remembered through the problem solving, okay. So that is the basic criteria of cracking chemistry to the best level, okay. So let us take some example to understand, okay. So we are going to talk about a preferential discharge theory. So basically preferential discharge theory says that, okay, if there are more than one type of cation or anion in the electrolytic solution, then that ion would be discharged which requires least energy or discharge potential, okay. So this is the same thing which I have just spoken about. So if in a solution there are say 2 cations, okay, now out of the 2 cation only one will get discharged, that cation would get discharged first which requires less energy to get discharged, or it requires less discharging potential. Okay, so that when we are connected with the battery, as soon as we give some current to it, okay, because its discharge potential is less, it will easily get reduced or it will easily get oxidized. Okay, so hope this is clear to you. So let us look at the basic data. Okay, so this is again taken from the electrochemical series only. Okay, so if you look at this, potassium plus is at the top and Ag plus is at the bottom. Now H plus is somewhere over here. We know that the reduction potential of H plus is 0. Okay, so you can also use a basic logic that suppose you are taking potassium. Okay, now potassium is a metal. Metals have the tendency to get oxidized, right? We know that all the metals have the tendency to get oxidized. Because metals are easily oxidized, so they will have a positive oxidation potential. So group 1, group 2 metals have positive oxidation potential. That means the reduction of the cation would not be so easy or would not be so spontaneous, because their reduction potential would become negative. Okay, so the reduction potential of these ions are negative, hydrogen is 0, and then the reduction potential becomes positive. Okay, so basically we have arranged them in the increasing order of their reduction potential. So we will say that as we go down the group, okay, in this series, the tendency of these species to get reduced is very high. So their tendency to get deposited at the cathode becomes very high, and easily they deposit at the cathode. So you have to remember few data. Okay, so H plus is having 0, copper 2 plus, we have already done so many questions that the reduction potential of copper 2 plus is 0.34 volt. This we are also going to study in transition elements. Okay, then Ag2 plus, then Ag plus. Okay, Ag plus is basically having a reduction potential of 0.8, that also we have done in lot of question. Okay, so when I am talking about reduction potential, obviously I am talking about standard reduction potential. Okay, K plus is having negative, calcium 2 plus, sodium plus, Mg2 plus, Al3 plus, zinc 2 plus, iron 3 plus, nickel 2 plus, Sn4 plus, Pb2 plus. All of them are having negative reduction potential. Okay, so suppose if in a solution there are two cations, suppose we are having say iron 3 plus and say we are having copper 2 plus. Okay, so we are having iron 3 plus and say we are having copper 2 plus. Okay, now out of these two species, which has more tendency to get reduced? We know that copper 2 plus is having more reduction potential. Okay, so it will be easy to reduce, whereas iron 3 plus, if it reduces into iron 2 plus, we know that its reduction potential is negative. Okay, so out of the two cation, if it is present in the same solution, if you pass a current, the tendency of copper 2 plus to get reduced would be more, and hence we will say that the copper 2 plus would get deposited at the cathode. Okay, so this is your electrical preferential discharge theory. Okay, so that ion is discharged first, which requires least energy or has a less value of deposition potential. Okay, so deposition potential of copper 2 plus we can say is less. Okay, suppose I can ask you one more question on this. Okay, suppose in a solution we are having say H plus and say we are having Ag plus. Okay, now you can see that the tendency of Ag plus to get reduced is more than that of H plus. Okay, its discharge potential is also less, so Ag plus would be preferentially discharged at the cathode. Okay, now one thing which you should understand over here, okay, if you are continuously sending electron, or if you are continuously sending, if you are continuously applied a potential difference between the two electrodes. Okay, now if the concentration of one of the electrode is completely consumed, suppose there was say C1 concentration of Ag plus and C2 concentration of H plus. Now when you are passing current, we know that Ag plus will get deposited as silver on the cathode. Okay, so after some time what will happen, the Ag plus will get completely consumed and it will not be available in the solution. If you still keep on sending the current in the solution, now what will happen, H plus will have to discharge as hydrogen gas. Okay, so you need to understand the external EMF which has been given to you. Okay, so we can discharge all the ions that is present in the solution preferentially, okay, or we can also discharge only one of the ion depending upon how much potential we have applied from external circuit. Okay, I hope this is clear to you. Now let us look at the anion for the same. So if you see that F negative, sulfate ion, nitrate ion, Cl negative, Br negative and OH negative. So their tendency to get discharge at anode increases. Okay. So if in a solution, say suppose we are having nitrate ion and say I negative ion. So we know that I negative has more tendency to get discharge and has a less value of discharge potential. So I negative would be oxidized preferentially as compared to say sulfate or nitrate. Okay. But if you are just like allowing the current to flow for a longer time, so it might happen that all the iodide ion in the solution is reacted or is oxidized and there is no iodide solution left. Then at that time the preferential discharge of the other anion would start happening. Okay. So this is the point that you should keep in mind. Okay. So let us look at an example to understand this. Suppose in a container, okay, suppose we are having a container or a electrolytic cell. Now suppose in this we are having say aqueous KCl, aqueous say CuCl2, okay, and suppose these are the two salts that are present in this solution. Now we have dipped two electrode in it, we have connected it with an external battery, okay, so we have connected it with an external battery and we are passing current into the solution. Okay. So what will happen over here? The first thing that would happen is KCl would dissociate into K plus and Cl negative. Okay. Similarly CuCl2, okay, would dissociate into copper 2 plus aqueous and 2Cl negative aqueous. Now because it is an aqueous solution, so aqueous solution will definitely contain water. So water will also dissociate into H plus and OH negative. Okay. So the question will come over here, which cation would be deposited first at the cathode. Okay. So we know that at cathode a reduction happens. Okay. So there are three ions that are competing with each other to get reduced. Okay. So out of these three cations, okay, that cation would be reduced first which has more positive reduction potential. Okay, because that reaction would be more spontaneous, or that cation would discharge first which is having less discharge potential. Now if you look at this chart, okay, you can clearly see that, okay, K plus is over here, copper 2 plus is over here and H plus is over here. Okay, now you can see that the tendency of copper 2 plus to get discharged or to get deposited at the cathode is much more than the other two ions. So preferentially what would happen? Copper 2 plus aqueous would take up the electron and get reduced and change into copper solid. Now this copper solid would get deposited at the electrode, okay, at the cathodic electrode. Okay. Now suppose you are sending more and more current, so it might happen that all copper 2 plus are consumed. Now in the solution copper 2 would not be present, so it will be left with K plus and H plus. Then when all the copper 2 plus is consumed, then after that H plus will get reduced because H plus is having more positive reduction potential, it is having zero reduction potential or it is having less, okay, discharge potential. So after that H plus would get reduced, 2H plus would take up 2 electron and change into a hydrogen gas. Okay. Now similarly if you look at anode, so what would happen at anode? We know that at anode there are three ions, there are only two ions that are competing, one is Cl negative and the other is OH negative. Now out of Cl negative and OH negative we know that the tendency to discharge at anode of OH negative is greater than that of Cl negative. So OH negative would discharge at the anode. Okay, so there are some basic reactions that you have to memorize as well. So as we will keep on exploring all these concepts, you will encounter so many reactions. Some reactions are important, I will specifically point which reactions are important and you should remember them. Okay. So when you take this, you evolve O2 gas, okay, and 4 H plus gas, okay. or you can rather take this as 2. Okay, so 2 OH negative will give us O2 gas plus 2H plus. Okay, so there are 2 negative charge over here and a 2 positive charge over here. So you have to add 4 electron over here so that the charges on both reactant and product are same. So at anode, O2 gas would be evolved. At cathode, copper would start depositing at the cathodic electrode, and at anode, O2 would be evolved at the anode. Okay. Now this cathode or the anode is a non-participating one, or a inert electrode. So they are not participating in the reaction. If this is a reactive electrode, then that can also undergo oxidation reduction. Then we have to consider that also. So we have to compare again its data also. Okay. So I hope this is clear to you. So you need to remember this. Okay. Fluoride, sulfate, nitrate, chloride, bromide, iodide, and OH negative. So this is easy to remember. Okay. Start with fluoride, chloride, bromide, iodide. You are going down the group, and the bottommost is OH negative. Then you have to just fix sulfate and nitrate in between them. Okay. Similarly, if you look at this, H plus, okay, copper 2 plus, Hg2 plus, Ag plus, K plus, calcium 2 plus, sodium plus, magnesium 2 plus, Al 3 plus, zinc 2 plus, iron 3 plus, okay, nickel 2 plus, tin 4 plus, and lead 2 plus. Okay. So I hope this is clear to you. I will give you a mnemonics for this as well. Okay, when we are about to complete the chapter, but initially I am not giving you any shortcut techniques. I want you to do the chapter holistically so that you understand each and every concept and you start focusing on the memorization as well. Okay. So let us start with the electrolysis of molten pure salts. Okay. Now when we are taking molten pure salts, okay, suppose we are taking say only NaCl and we are melting it. So the solution would be called as molten NaCl. Now when you pass current through it, it will give us cation Na plus and anion Cl negative. There are no interfering, or there are no cations or anions that are competing with them for oxidation or reduction. So what would happen? The cation of the salt would undergo reduction and the anion would undergo oxidation. So the example of this is molten or fused calcium chloride. So when you have taken molten or fused calcium chloride, so it does not contain any water. So calcium chloride will basically split into calcium 2 plus and 2 chloride ion. Now this calcium 2 plus would go at the cathode and undergo reduction, getting releasing calcium solid. So this calcium would start depositing at the cathodic electrode. Okay. Similarly at the anode, chloride ion would migrate and chloride ion would undergo oxidation. Chloride ion on oxidation gives us the chlorine gas and 2 electrons are evolved. Okay. So overall reaction we can write, we can just add them. So we will say that calcium chloride is giving us calcium solid that is getting deposited at the cathode and chlorine gas is evolved at the anode. Okay. So I hope this is clear to you. So electrolysis of molten pure salt, we say that cation will get reduced and anion will get oxidized. There are no competing reactions because there is only one fused salt. Okay. So the cation would get deposited at the cathodic electrode as a solid, and at anode generally gas evolution takes place. Okay. So let us take another example. Now this is again a very important reaction. This we will encounter when we are studying metallurgy. Okay. This is used for the purification of aluminum. Okay. So when we are carrying out the metallurgy, we need to prepare the metal in the purest form. Okay. So when we have extracted the metal, okay, we will just do the electrolytic reduction so that we get pure aluminum. Okay. So what we do is we take molten Al2O3 and now we have taken graphite electrode in it. Okay. So you have to remember this when we are doing the electrolysis of Al2O3, aluminum trioxide. Okay. So what we are doing, we are taking a graphite rod, okay, and we are just dipping it in the molten Al2O3 solution. We are passing the current. Okay. So Al2O3 will dissociate into 2 Al3 plus 3 O2 negative. Okay. Now we know that at cathode Al3 plus would migrate and would get reduced into aluminum solid. Okay. So 2 Al3 plus which was there in the melt would take up 6 electron because total positive charge is 6. So this will take up 6 electron and convert into aluminum solid. Okay. So that aluminum would start depositing at the electrode, the cathodic electrode, okay, which is a graphite rod. Similarly, if you look at the anode, Now we know that the anode was made up of graphite electrode. Okay, so we know that anode has carbon on it. So the anion, which is O2 negative in this case, oxide ion, will migrate towards the anode. Now when it migrates, it will combine with the carbon of the electrode. So it combines with the carbon of the electrode and forms CO first. Okay, or it can also combine with more amount of O2 negative oxide and form CO2. Okay, so if you add all these reactions, okay, so we'll get Al3 plus 3 O2 negative plus 2 carbon forming CO2 plus CO plus 2 aluminum. So basically this is also known as Hoops process, which is used to purify the aluminum, okay, during metallurgical extraction. Okay, so we are taking Al2O3, we are dipping, okay, the graphite electrodes in it, and we are passing current. So at cathode nothing different would happen. Al3 plus would get reduced and Al would get deposited at the cathode. But at anode, the carbon of the graphite would react, forming CO and CO2 gas. So this is again a important reaction that you should know. Anyways, we are also going to cover this when we are doing metallurgy. So this is an important portion. Let us talk about K2SO4. Okay. Now if we take K2SO4, K2SO4 first will break into K plus and sulfate ion. The K plus or the potassium ion would go at the cathode, take up an electron and convert into potassium solid. So at cathode, potassium would get deposited. Now at anode, sulfate ion would undergo oxidation. Now whenever sulfate ion undergoes oxidation, it forms peroxo disulfate ion. So 2SO4 2 negative would undergo, okay, oxidation and form peroxo disulfate, which is H2O8 2 negative plus 2 electron. Okay. Now this H2O8 2 negative is a very important reagent in analytical chemistry. Okay, because if you look at the reverse reaction, so H2O8 2 negative would be taking up 2 electron and changing into sulfate. So it is undergoing reduction. So it is an oxidizing agent. So we'll study this when we are doing the transition elements. Okay, H2O8 2 negative directly converts Mn2 plus into MnO4 negative. Okay, so these are the basic points that we'll be doing in inorganic chemistry. Okay, so at anode we'll say that H2O8 2 negative is getting liberated, and at cathode potassium would be deposited at the electrode. Okay, so the overall reaction you can just add it. Okay, cancel out the electron, so we'll get K2SO4 changing into potassium plus H2O8 2 negative. Similar would be the case with any of the sulfates of metal. You take Na2SO4, you take Li2SO4, you take calcium sulfate, you take magnesium sulfate. Okay, any of the sulfates you are taking in molten form, okay, the metal would get deposited at the cathode and the anion would get oxidized into peroxo disulfate ion, and that would remain in the solution near the anode. Okay, so I hope this is clear to you. Okay, next comes is the sodium thiosulfate. Okay, now we know that sodium thiosulfate is also called as hypo. Okay, as soon as you will hear the word hypo, you must connect it with the iodometry and the iodometric titration. Okay, so this is again a very important reagent, okay, and a very important compound for your titrations. Okay, so when you take Na2H2O3 and pass current through it, so it will first dissociate into Na plus and H2O3 2 negative. Okay, so that is what we are getting. At the cathode, Na plus would migrate. Okay, it would take up the electron and change into sodium solid. At anode, H2O3 2 negative would undergo oxidation and form S4O6 2 negative plus 2 electron. Okay, so remember this reaction we were using in iodometric titration. Okay, we were producing iodine in the solution and we were titrating it with a standard hypo solution. So that iodine was reacting with hypo and forming I negative plus S4O6 2 negative. Okay, so thiosulfate on oxidation gives us tetra thionate ion S4O6 2 negative. Okay, so when you just multiply 2 with this reaction so that the number of electrons on both the sides become same, just add it, so we'll get this as the final reaction. Okay, so I hope this is clear to you. Now let us take the example of electrolysis of molten mixture of salts. Okay, so again we are having two salts. Okay, so they will dissociate and give two cations and two anions. Now out of the two cation, that cation would be discharged first, which is having more positive reduction potential or less discharge potential. Similarly, out of the two anion, that anion would be discharged at the anode, which is having more positive oxidation potential or less discharge potential. Okay, so let us take example of molten or fused NaBr or MgBr2. Okay, now NaBr would break into Na plus and Br negative. MgBr2 would break into Mg2 plus and Br negative. So anion is common, so there is no issue about anion. So only one kind of anion is present, so that would migrate towards anode and undergo oxidation to form bromine gas. Now if you look at the cation, now there are two types of cation, Na plus and Mg2 plus. Okay, now we know that the reduction potential of Mg2 plus is less negative than that of Na plus. So the tendency of Mg2 plus to get discharged or to get reduced is more. So Mg2 plus would reduce into magnesium solid and would get deposited at the cathode. Okay, so remember this series, I have already shown you this series. Okay, you can see that out of Mg2 plus and Na plus, okay, Mg plus has the more tendency to get discharged. Okay, so the tendency of discharge increases as we go down the group. Okay, I hope this is clear to you. So these are the basic questions that can be formed on the product of the electrolysis. Okay, okay, so let us look about the aqueous solution now. So we want to talk about electrolysis of electrolyte in aqueous solution. Now this is very important, you need to know all the important reactions over here. If you know all the reactions over here, then believe me, the problem solving on this chapter is a cakewalk. You won't find any difficulty in solving the questions if you are clear with what reactions are happening at what electrode. Okay, so the first example is we want to take an aqueous solution of NaCl. Okay, now we know that when we are passing current, okay, so NaCl would break into Na plus and Cl negative. So there is a tendency of Na plus to get reduced and Cl negative to oxidize. But because it is an aqueous solution, now in aqueous solution water is also present. So water would break into H plus and OH negative ion. So now there are two types of cation, Na plus and H plus, that could get reduced at cathode. Out of the two, we know that H plus is having 0 reduction potential, whereas Na plus is having a minus 2.8 standard reduction potential. So obviously the tendency of H plus to get reduced is more. So H plus would get reduced first and would evolve hydrogen gas. Similarly, we have to see for the anions. Okay, but if you look at the reaction, we are not writing. So we are saying that there are two interfering anions, two interfering cations, Na plus and H plus. But at the cathode, we are not writing H plus. We are writing reduction of water only. Okay, so this is a point that you should understand. When you have dipped an electrode in a solution, okay, that is having a cation as well as an anion. Okay, so there is a cation that can reduce, there is a H plus that can reduce. But if you look at the value of Kw of water, that is very small, 10 raised to minus 14. So if you pass electric current through water, so the number of H plus ion produced would not be much. It would be a very small value. Okay, but because water is present in excess quantity, because it is an aqueous solution, so there would be the tendency of water to get reduced itself. Okay, so that is why we are not going to consider H plus reduction. We are going to consider reduction of water. Okay, because that is present in large quantity. Okay, so Na plus when it undergoes reduction, it forms sodium solid. We know that the reduction potential is minus 2.71. When water undergoes reduction, it gives hydrogen plus OH negative. The reduction potential is minus 0.83. Now out of the two reactions, which reaction has more tendency to happen at cathode? We know that the reduction potential of water hydrogen is less negative. So this would be the main reaction that is happening at the cathode. Okay, so water would get reduced. Okay, so you have to remember this reaction. Okay, if you remember this reaction, questions will be very easy to solve. Now if you are reducing H plus ion, okay, if we were considering that this solution had Na plus and H plus as the cation which was trying to get reduced at the cathode, out of the two cations, H plus would get reduced and form hydrogen gas. Okay, now when water is also reducing, okay, it is getting reduced, hydrogen gas is evolved. So the product does not change. Okay, so you have to remember that way, when water is undergoing reduction, you have to form hydrogen. Now if you try to balance, obviously you need to evolve OH negative. So water would take up 2 electrons and form hydrogen gas plus 2 OH negative. Because its reduction potential is less negative, so this would have the more tendency to get reduced. So at cathode, hydrogen gas would be evolved. Now let us look at the anode. Now in anode we know that there are two ions that are interfering. Okay, one is Cl negative, that can get oxidized into Cl2. If we consider the dissociation of water, then we had OH negative. And remember, the series started with F negative, Cl negative, Br negative, I negative, at last there was OH negative. Now after F there was sulfate and nitrate ion. So the tendency of OH negative to get oxidized was more than that of Cl negative. Okay, so when OH negative oxidizes, we know that O2 is the product. Okay, so chloride ion would get oxidized to form Cl2, and at anode now OH negative is also there, but again the concentration or the number of OH negative near the anode, near the electrode is less, so we'll take the complete oxidation of water itself. Okay, so the water can get oxidized, it will again evolve O2 gas. Okay, so water would evolve O2 gas, 4H plus ion and 4 electron. Okay, now if you look at their potential values, okay, their standard oxidation potential, okay, so you can see that, okay, out of the two value, the oxidation potential of water is less negative. So we should say that, okay, evolution of O2 should take place at the anode. Okay, so this is what we are saying. Okay, so at cathode hydrogen gas should be evolved, and at anode we are saying that O2 gas should evolve. Okay, but here is a catch. Okay, so these are the anomalogy where you should understand, okay, that we have to keep focusing on these short or the important points. Okay, so you need to understand the regular trend as well as irregular trend. Irregular trend, according to me, is more important than the regular trend, because questions are mostly formed on irregular trend. Okay, so if we come back to this reaction, now we say that there is a concept of over potential over here. Now what do we mean by over potential? Okay, so I am talking about the term over potential. Okay, now the formation of O2 from water is kinetically slow. Okay, so the reaction is not fast, it is slow. So to make this reaction happen, okay, we need to apply additional voltage or the extra voltage so that O2 gets evolved. Okay, so O2 does not get evolved at this particular data, okay, at minus 1.23 volt. We have to increase the voltage so that O2 evolution takes place. That additional, okay, potential that is required for this O2 to discharge from the water is known as over potential. Okay, so we say that the formation of O2 from water is kinetically slow. So to evolve O2, we need to apply additional potential. Okay, that potential is known as over potential, due to which this reaction does not takes place, okay, and the evolution of Cl2 happens. Okay, so on looking the data, we can directly say that this should get oxidized. Okay, but this is getting oxidized because this needs more potential, okay, to get oxidized. So that is the case of over potential. So over potential you have to observe only in the case of oxidation of water. Okay, there are more cases, this is not like this is the only case, okay, but for JEE standard we need to remember this. Okay, so if you look at the overall reaction, okay, so we know that at cathode, okay, hydrogen gas is evolved, okay, and at anode we know that Cl2 gas is evolved. Okay, I hope this is clear to you. Now these are the two primarily reaction that is happening. So when you add them, these electron will get cancelled out. So eventually the final reaction which we will be getting over here is, okay, if you add, okay, we know that this reaction would be happening, this reaction would be happening. So when you add them, so we'll say that 2H2O plus 2Cl negative aqueous is forming Cl2 plus hydrogen gas, okay, plus 2OH negative gas. I hope this is clear to you. So this is the overall reaction that is happening. Now look at the beauty of this reaction. Now how many different type of questions can be framed on one particular electrolysis reaction? The first question that could come over here is, what are the gases that are evolved at cathode and anode? Okay, so we know that at cathode hydrogen is evolved, at anode Cl2 would be evolved. Now second question that could come over here is, you will be given certain quantities and you will be asked to find the volume of the hydrogen and the O2 gas liberated. Okay, Third question that can come is, after electrolysis of NaCl, the solution will have a pH greater than 7, less than 7, equal to 7. Now if you look at the main reaction, okay, the overall reaction, in this reaction we can see that OH negative is produced in the solution. Okay, now because OH negative is produced, we can very well guess that the solution would become basic. So the pH of this solution would be greater than 7. Now you can also get a question where you have to find the pH of the solution after electrolysis. So certain quantity would be given to us. We will use Faraday's law to get the number of moles of OH negative. We can get the concentration if volume is given to us. Through concentration we can find it the pOH. From pOH we can find the pH. So these are the basic 3 or 4 types of question that is formed on this electrolysis portion. Okay, so you need to understand the reaction first. Okay, so all these reactions are very critical and you need to know all these reactions. Okay, now let us come to the second portion of this. Is we are doing the electrolysis of very dilute solution of NaCl. Okay, so again same thing, we will say that at cathode there is a Na plus. Now we will not say that there is a H plus, there is a water that can reduce. So Na plus can get reduced, water can get reduced, the tendency of water to get reduced is more and hydrogen gas would be evolved. Okay, so this is what we have done in the previous also slide. Okay, if you look at the anode, now in the anode, in a normal solution we were saying that O2 was not getting evolved due to the concept of overpotential and Cl2 was getting evolved, even though the thermodynamic data predicted that O2 should be evolved. Okay, but when you take a very dilute solution, okay, so if you look at the EMF of this Cl negative Cl2 oxidation, okay, so we will say that EMF oxidation potential of this particular reaction would be standard oxidation potential of Cl negative changing into Cl2 minus 0.059 upon N we know is 2 into log of partial pressure of chlorine divided by concentration of Cl negative whole square. Okay, so we have just applied the Nernst equation to get the potential or the EMF of this half reaction. Okay, now when we have taken a very dilute solution of Cl negative, so we know that this concentration would be very small. Okay, we have raised it to the power 2, so that would become even more small. Now when you take a reciprocal, so obviously this will go above and this quantity would increase drastically. Okay, so when you take this, okay, so the E of this would come to be, okay, much more negative than minus 1.36. So the difference between the two would increase drastically. Okay, so suppose 10 raised to the minus 5 molar solution you have taken, so this will be 10 raised to the minus 5 raised to the power 2. Okay, so that would be 10 raised to the minus 10. Okay, now when this goes above, okay, so this would become 10 raised to the power plus 10. Okay, now when you take this outside, so this would be 0.059 into 10 divided by 2. Okay, so obviously this is minus 1.36, so another negative term would come, so this would become more negative. Okay, so the gap between the two value would increase. Okay, I hope you have noticed this gap is very small, 1.23 and 1.36 with a negative sign. Okay, so over potential concept was applicable. Okay, but when you have diluted the solution, the EMF at which chloride ion would get oxidized has decreased. Okay, it has become more and more negative, so the difference between the two would increase, due to which even though after over potential O2 would be evolved. Okay, so for a very dilute solution we will say that at cathode hydrogen gas is evolved and at anode O2 gas would be evolved. Okay, I hope this is clear to you. So if you add the two reactions, okay, so we will see that overall 4H plus are produced from here and 2H negative are produced from here. Okay, so overall the solution would be acidic in nature. Okay, so there is one more concept that is often quoted in the books, which says that because we have taken a very dilute solution, so the number of chloride ion in the solution would be very less as compared to the number of water. So that is why water would be preferentially discharged as compared to Cl negative. That is also correct, but this is a better and a thermodynamic explanation of the concept. So when you dilute the solution, the EMF at which chloride ion get oxidized would decrease further. Okay, so even after overpotential, the gap between the two would increase drastically and O2 would be evolved. Okay, but under normal conditions, O2 is not evolved and Cl2 would be evolved because of overpotential concept. So this is again a very important concept that you should know. Okay, third comes is the aqueous solution of Na2SO4 solution using inert electrode. Okay, so Na2SO4 again would dissociate into Na plus and sulfate ion. Okay, so at cathode we'll say that reduction of Na plus and reduction of water can take place. Okay, the reduction potential of water is less negative, so reduction of water would take place. So at cathode hydrogen gas would be evolved. Okay, now if you look at anode, so we know that in anode sulfate ion can undergo oxidation, so it can change into tetrathionate ion. Okay, the oxidation potential is minus 2.01 and water can get oxidized, okay, as O2 gas. Now you can see that there is still the concept of overpotential, but the gap between the two is very large. Okay, so even at this potential, O2 would get liberated. Okay, so the overall reaction, we'll say that in this reaction 4 water, okay, if you add them, okay, we'll say that 4 water are reacting together and forming O2 gas plus H2 gas plus 4H plus 2OH negative. Okay, I hope this is clear to you. Okay, so we'll say that at anode O2 gas is evolved. Now you can cancel for balancing. We'll say that 2OH negative you can combine with 2H plus and we'll form 2 water. That 2 water will be cancelled with 2 water, so we'll be left with 2 water changing into O2 plus H2 plus 2H plus. Okay, so I hope this is clear to you. So if you do the aqueous solution of lithium sulfate, electrolysis of aqueous solution of lithium sulfate, potassium sulfate, calcium sulfate, magnesium sulfate, aluminum sulfate. So in all these cases, the same product would be obtained. At anode, we'll always get the reduction of water. Okay, hydrogen would be evolved, and at anode, water would be oxidized, and we'll get O2. Okay, so O2 gas would be evolved. So this is when we are doing it with the inert electrode. Okay, so let us come to a very important aqueous solution of copper sulfate. Now if you will browse through many of the textbooks or the materials, you will get a lot of question on the electrolysis of copper sulfate. Okay, so we are doing the electrolysis using inert electrode, say something like platinum. So we have passed electric current through copper sulfate, we'll get copper 2 plus and sulfate ion. Okay, now copper 2 plus will migrate towards cathode. There should be H plus also that is migrating towards the cathode because it is aqueous solution, but H plus is very small. H plus is present in very small amount and water is present in excess amount, so we will write the reduction of water only. So copper 2 plus when reduces gives us copper. Okay, if you remember the series, copper was below the H plus, okay, in the discharge potential, okay, data. So the tendency of copper 2 plus to get reduces more. So copper 2 plus would reduce in this case, okay, because it is having a positive reduction potential, whereas the reduction potential of water is negative. Now if you look at the sulfate ion, now we have already done this. Out of sulfate ion, OH negative, tendency of OH negative to oxidize is more, so O2 will be evolved. But again, we will not show the oxidation of OH negative, rather we will show the oxidation of water. So water on oxidizing, okay, 2 moles of water on oxidizing will produce 4H plus 4 electron plus O2 gas. Okay, so the overall reaction of this would be copper 2 copper 2 plus 2 water changing into 2 copper plus O2 plus 4H plus. So again, this solution would be, the resulting solution after electrolysis would be acidic in nature. Okay, because H plus is getting released in this reaction. Okay, so again a question can be framed on this, that find the pH of the solution when we are, say, 0.1 molar of copper sulfate is electrolyzed for certain time using certain charge. Okay, so these kind of question we will cover in the next class when we study about the Faraday's law. Okay, so I hope this is clear to you. Okay, now let us look at the electrolysis of copper sulfate solution using copper electrode only. So what we are doing over here, we have taken copper sulfate solution. Okay, now in that solution we have dipped the copper electrodes. One is acting as a cathode and the other is acting as a anode. Okay, so in the copper sulfate solution we have dipped a copper cathode and a copper anode, and we have connected it with the external battery and allowing the current to go into the solution. So we know that copper sulfate would dissociate as copper 2 plus and sulfate ion. At cathode, copper 2 plus can undergo reduction, okay, because at cathode reduction happens. H plus would be there because it is aqueous solution, so water would be dissociating into H plus and OH negative ion, but because the concentration of H plus would be very less in the solution, so we will consider the reduction of water itself because that is present in the large amount. So water would get reduced and we will get hydrogen gas. Okay, out of these two data, we can easily guess that copper 2 plus would be reduced first and it would be deposited at the copper electrode. Okay, because it is having more positive reduction potential. Now let us look at the anode. So in anode we know that sulfate ion would migrate and it can oxidize to give tetrathionate ion, okay, the oxidation potential of which is minus 2.01. Similarly, OH negative, if solution is aqueous, so water was breaking into H plus and OH negative would go at the anode and evolve O2. But we will not consider OH negative, we will consider water as a whole because the amount of OH negative in solution would be less. Okay, so water would undergo oxidation and would give us O2. Okay, now the oxidation potential of this is minus 1.23. Now because we have not taken a inert electrode, we have taken an active electrode or a participating electrode. So at anode, the oxidation of the electrode can also take place. Okay, so at cathode, copper can also get oxidized. So when copper oxidizes, it will change into copper 2 plus and 2 electron would be evolved. Now the reduction potential of this was 0.3 volt. So oxidation potential would be minus 0.34 volt. Now you can clearly see the three data. The oxidation potential of copper changing into copper 2 plus is much more than that of sulfate and water. Okay, this is having less negative value. Okay, so in this case the oxidation of copper will take place. Okay, so you can look at this. This is a very important question. This is often used in metallurgy for the purification of metals. Okay, we will discuss, okay, just like the Hall-Héroult process of aluminum which I already told you, okay, with carbon electrodes. Similarly, this would be the electrolytic reduction of copper forming copper. Okay, so in this case we will say that, okay, at anode copper is getting oxidized and at cathode copper 2 plus is getting reduced. Okay, so in this case there won't be any concentration change of copper 2 plus because whatever copper 2 plus is getting reduced at cathode, similar amount of copper 2 plus would be generated from anode. So this is a very important point. So whenever you are taking any electrolyte and you are dipping it in a solution, taking the electrode as a active electrode and not an inert electrode, then you have to consider its oxidation as well. Okay, so these are the few points that you should remember. So in this case copper 2 plus is getting reduced and copper 2 plus is getting formed at the anode. Okay, so I hope this is clear to you. So due to this there won't be any concentration change of copper 2 plus in the solution. Okay, so let us look at another reaction which is electrolysis of AgNO3 using platinum electrode, which is the inert electrode. So we know that at cathode Ag plus or water can get reduced. Ag, if it get reduced, it will form silver, okay, that would get deposited at the cathode. Okay, water has the reduction potential which is negative, so Ag plus would be discharged at cathode, and at anode water would be oxidized. Okay, nitrate, generally we say that because nitrogen is in +5 state, so nitrogen is already in its highest oxidation state, so it cannot oxidize further. Okay, so at anode the oxidation of water would take place and we will evolve O2 gas over there. Okay, so the overall reaction of this would be Ag plus, okay, you have to multiply this with 4, okay, so that when we add them the electron get cancelled. So 4 Ag plus 2 water is changing into 4 Ag plus 4 H plus O2. Okay, so we will say that at cathode silver is getting deposited, at anode O2 is getting evolved. Okay, I hope this point is clear to you. Okay, I hope this point is clear to you. So again in this we will say that after the electrolysis of this solution, the solution will become acidic in nature. Okay. Now let us look at another case, that is aqueous solution of AgNO3 using Ag electrode. So this is not an inert electrode, so this is a participating electrode or a active electrode. So when you have dipped silver rod in the silver nitrate solution and passed current through it, silver nitrate would decompose into silver plus and nitrate ion. So at cathode, silver ion can get reduced and water can get reduced. Silver ion, we know that has a positive electrode potential, so positive reduction potential, so Ag plus would be reduced, okay. And at anode, we know that nitrate cannot undergo oxidation, it is already there in its highest oxidation state. Now when we oxidize water, okay, O2 will be liberated, its EMF is minus 1.23 volt. Now when silver gets oxidized, because the rod is silver only, okay, the anode is made up of silver material, so the oxidation of silver can also take place, so this can oxidize into Ag plus and electron. Now the oxidation potential would be negative of the reduction potential, which is minus 0.8. Now you can clearly see that this is, okay, less negative, so the tendency of silver to get oxidized would be more, okay. So at cathode, what is happening, Ag plus is getting reduced and Ag would be deposited at the electrode, okay, and at the anode, the Ag of the anode would oxidize and enter into the solution as Ag plus. So whatever Ag plus was depositing at the cathode would come back into the solution through anode via oxidation. So in this case, we will say that there is no change in concentration of silver ion in the solution. Okay, I hope this is clear to you. Okay, I hope you are taking a snapshot of this as well. Now let us look at another important electrolysis, that is aqueous solution of H2SO4 solution. Okay, so we are taking a dilute acid, okay, dilute H2SO4. So we know that when we add acid into a water, so acid will furnish H plus ion, okay. Now H plus ion can get reduced at cathode because there is a lot of water, water can also get reduced. Reduction potential of H plus is 0, whereas the reduction potential of water is negative. So preferentially H plus would get reduced and hydrogen gas would be evolved, okay. Similarly, if you look at anode, sulfate ion can undergo oxidation forming tetrathionate ion, EMF is minus 2.01, okay. But when water undergoes oxidation, it will form O2 gas and its oxidation potential is minus 1.23. So in this case, okay, the oxidation of water would take place, okay. So we will say that at cathode H2 is evolved and at anode O2 is evolved, okay. I hope this is clear to you. Okay, I hope this is clear to you. So overall, what would be happening? Water is breaking into H2 and O2, okay. So when you add the two reactions, we have to multiply this reaction with 2, okay. So you have to multiply this reaction with 2. Now you will add these two reactions, okay, you will see that you will get H2 and O2 as the product, okay. So during the electrolysis of H2SO4, we will get H2 and O2 as the product. But when we are using high current density, so you have to remember this point again, this point is taken from NCERT, so this is important, high current density, or we are taking high concentration of H2SO4. Now because concentration of H2SO4 is more, so the concentration of sulfate ion would be more, okay. Now because the concentration is more, number of ions is more, so near the anode the number of sulfate ion would be more, so the tendency of sulfate ion to get oxidized would be more. So in that case, okay, H2O8 2 negative would be formed at anode. Okay, I hope this is clear to you. I hope you have understood this well. Okay, so there was one coal-based electrolysis process that I wanted to discuss. Anyways, I am going to discuss it tomorrow. I think there is some doubts that you have posted over there, so I will take up those doubts. Okay, so we are left with only coal-based electrolysis process that I am going to discuss tomorrow, and tomorrow we are going to start with Faraday's first law and Faraday's second law, and we are basically going to do a lot of problem solving because Faraday's laws are very small. Okay, we just need to know the rule and we'll start solving the questions. Okay, the questions will be based on these reactions only. So you need to understand all the reactions, you need to understand the reactions that would be happening at the different electrodes. Okay, I hope you understood everything that was taught today. You can also read NCERT or any textbook that you are following. Okay, always complement your classes with a theoretical reading. That will actually help you increase your brain power and you will be able to hold a lot of content in your brain. Okay, so I open the class for Q&A. So if you are having any doubt, you can post it over there so that I can take it on a live platform. Yeah, so I think someone gave a question on organic chemistry by mistake. Okay, Tanmay, what you can do is you can post the doubt on the platform. I will answer you like after the class, because I want to take up the physical chemistry question first. I want to have a look on those questions if anyone is facing any doubt on this chapter. This is a very easy question. Okay, you just have to consider the geometrical isomers of this, this and this. Okay, because anyways if you look at this carbon, okay, because all three groups are same. Okay, so if suppose one is cis and the other two is trans, or one is trans, other two is cis. So this will always be optically inactive. So this carbon is always optically inactive. So you don't have to check for the optical isomers. You basically have to check for the geometrical isomers. So you can like write, there are 3 double bonds. So their maximum 8 isomers is possible. So you have to write all the cases that this can be EEE, okay, EEZ, ZEE, EZE, ZZZ, ZEE, okay, ZEZ and EZZ. Okay, out of those you have to take out the common cases. Okay, you can see that and you can find the number of isomers. Okay, so I will solve this question and send to you. Okay, personally I will send it to you. First I want to see if there is any physical chemistry doubt to be catered, because currently we are dealing with a physical chemistry chapter. Okay, so can you show me the next question please? Okay, Tanmay, which of the following is chiral? Tanmay, I will write to you. Let me see another question. Okay, this is again a very basic question of isomerism. Okay, so you have to check for the plane of symmetry for all the cases. Let me see if there is any more question. Okay, can you show me the next question? Okay, so again same organic doubt only. Okay, chalo, I will tell you one. I will send the doubts of the rest on the platform. Okay, I will just send it after the class. After 10 minutes you will get the doubts, you will get the answers. Okay, so we want to check which of the following exhibit geometrical isomerism. Now this is because of this is a single bond, so there is no bond rotation that is possible over here. Okay, so these two bromine cannot adopt a different configuration, so this is geometrically inactive. If you look at this, okay, so you can clearly see that there are two Me that are coming outside the plane, so they can be considered as a cis isomer. Now if one Me comes outside and the other goes inside, so that will become the trans form. So clearly you will say that A is geometrically active. Okay, now if you look at this one, okay, so we know that this is a spiro compound, the two rings are mutually perpendicular. Okay, so if you look at this case, so the two rings are mutually perpendicular. Okay, so this is, suppose this is going inside the plane and this bond is coming outside the plane. Okay, now there is a Cl over here. So if you consider something like this is one cyclic ring. Okay, this palm is a one cyclic ring, the other cyclic ring is mutually perpendicular to it. Okay, because it is a spiro arrangement. Okay, now if you look at this, there is one Cl that is going inside the plane. Okay, so suppose there is one Cl which is going inside the plane. If you look from forward, so there is one Cl that is going inside the plane, okay, or coming outside the plane you can say. Okay, so if you look at the other Cl, now this Cl can be either outside the plane or inside the plane. Okay, so if you look at this arrangement of atom just over here and over here, okay, so you can say that this Cl can either be coming outside the plane or going inside the plane. This Cl can either be coming outside the plane or inside the plane. Now are they having any different orientation? Then only we will say that it is having a geometrical isomer. So if you look at this, okay, so this ring is going inside the plane, so this Cl can either come outside. Okay, if you look from the front, because this bond is coming outside and that bond is going inside. Okay, so this carbon should have a tetrahedral arrangement. Okay, so one Cl can either go at the top, okay, and the hydrogen can go in the bottom. Okay, and if you look at this carbon, okay, if you look at this carbon, so basically if you are seeing this is a planar type of structure. Okay, so one Cl will come outside the plane or the Cl can go inside the plane. So if this Cl is coming outside the plane, okay, and this Cl okay, is coming outside. Okay, so it is coming outside. So we will say that they are cis isomer, and if this Cl is going inside, then we will say that is a trans with each other. So this can also exhibit geometrical isomerism. Now if you consider this again, we will say that this cyclic ring and this double bond, they will be mutually perpendicular to each other. So there is a cyclic ring and there is a double bond. Okay, you need to visualize this 3D structure on the paper itself. Now you can adopt different models. I basically try to do it through my hands and understand the orientation. You can do it by drawing the structures as well. Okay, so there is one cyclic ring and there is a double bond over there. Okay, now if you consider this double bond, okay, so there is a cyclic ring. Okay, let us assume that this is planar. Okay, so there is a Cl over here that can be outside, okay, coming outside the plane or going inside the plane. Now there is a double bond over here. Okay, now if you consider this double bond and this cyclic ring would be mutually perpendicular to each other. Okay, so when they are mutually perpendicular to each other, so if this is a cyclic ring, this would be the double bond. Okay, so the Cl which is attached to this carbon could either be on this side, okay, or it can be on the back side. So if this is on this side, okay, and this Cl is coming above it, or it is going inside the plane, so there won't be any change in the conformation. So this cannot show geometrical isomerism. A and B can possibly have geometrical isomers. Okay, so I hope this is clear to you. Similarly, I will write the doubts of your question just after the class, so don't worry about that. Okay, so in case you are having any physical chemistry doubt, because I would appreciate that more, if you are facing any problem in physical chemistry chapters that we are doing currently, just post to us so that we can get back to you.